So, hello, ladies and gentlemen. I'm very happy to be here with you today at the 12th Spanish Passive House Conference, and even more happy to be with you at the first ever virtual Spanish Passive House Conference. I hope you're all enjoying the format of the event this year. So, my name is Stephen Quinn. I'm both a Passive House consultant and certifier with Peel Passive House Consulting, located in Canada. And my presentation today is called Shifting Gears. And this is based on a project that's most definitely shifting gears, and that is the world's first passive house car dealership. So we'll give a bit of background on the project. The client was the Scottsvale Group, and the building itself was both a car dealership and repair shop. So the 3D floor area, approximately 1,500 square meters, and it was located in Red Deer, Alberta. And in Red Deer, as you'll see there, we have extremely cold design temperatures, so minus 29 degrees Celsius. We actually had a report from the client that last winter, a new record was broken for an extremely cold temperature of minus 42.5 degrees Celsius. So this passive house has most definitely already been put through its paces, and we were happy to discover that the client was very happy with the comfort levels in the building, even in these extremely cold temperatures. So the client's rationale behind going passive was that the passive house aligns with the Subaru environmental strategy. It was also inspired by Subaru's zero landfill factory in the US. And this is a family business for the client, and the owner saw this as a better way, basically, and saw it as a legacy project for his family business. Of course, having virtually no cost to heat or cool the building was quite appealing too. Now here we have a statement from the client himself, Garrett Scott, and he felt his building was an important statement to the industry and the country. So it's nice to hear when we have a client who recognizes that their building is not only having an impact on them, but also in the wider community. So we have a little bit of an overview on cold climate. As you know, this type of a climate, I imagine, is quite different to what you're experiencing in Spain. Of course, we have cold temperatures. And in these conditions, every decision matters more. One of the big factors we noticed was the air tightness and how it has a huge impact. So the early design stage, we played around with different air tightnesses for the building, and we realized that a small adjustment in the air tightness of the building in design stage, we could see already it had a massive impact on the energy demand. So we were very much focused on keeping our building airtight. Frost protection, of course, was a big requirement and required a lot of attention. And low humidity can become problematic in winter. The air can get very dry. So this is something that we also needed to be conscious of. Then the design temperatures themselves influence the functionality of the equipment. As you'll see later on in the presentation, we do have some equipment that couldn't meet or operate within the range we required. So we had to find alternatives. But yeah, the functionality of the equipment at these temperatures was another challenge. And then, of course, product availability. Not so many or no local manufacturers of cold climate products. So this made it very challenging. We did look to the European market, and then we found that some wouldn't export to North America. So there were some limitations there that we had to overcome with regards to product availability. And on the design front, we most definitely walked a fine line to meet the targets in this project. So we have the building design itself. It's pretty typical car dealership. It's 2 stories. It has a compact form, which we were happy to see with regards to passive house. And then we have the corporate image guidelines. So this is the southwest facade, and it was required by the client with regards to the corporate image to have this large glass facade here. Unfortunately, that's west facing. So that did cause us some challenges with regards to overheating of the building. But overall, the building itself, the compact form at least, was a benefit for us. So we'll have a look at the floor plans. Here we have the ground floor. So on the left-hand side, we have the showroom. Working our way to the middle, in red, we have some office space. This is the reception area here in the orange color. And then in green, we have the workshop area. So you'll notice a lot of the bays. There's 6 car bays here in the repair shop. And then to the south, we have the drop-off area where our clients would be dropping off and picking up their cars to be repaired. And onto the second floor, we have, again, on the far left, the showroom itself. This is an open plan. So this is open to the showroom, as is on the right to the repair shop. The majority of this area is open to below. There is some storage space up here. You can see a catwalk or walkway right down the middle of that area, but the remainder of this area is open. And in the center is predominantly red there. This is all the office space on the upper floor. So onto the opaque assemblies. You can see on the top left, we have our external concrete foundation wall. It's externally insulated with EPS, as were our pillars below. And both of them, we were looking to achieve U values of 0.11. That's what we achieved. And then on the roof and wall, when we had the opportunity to have more insulation, we took it. You can see possibly from the photo the thickness of our roof, which is completely insulated, and this allowed us to achieve a U value of 0.05 watts per meter square Kelvin. So quite a considerably low U value, lower than most typical passive houses. But again, we were dealing with an extreme climate. So both the roof and the wall with the 0.08, these were highly optimized building assemblies to allow the building to meet the passive house targets in this cold climate. Yeah, as you can see here, the wall was 300 millimeters LSL lumber, and it was insulated with dense packed cellulose, and externally then with 3 inches of rock board. And on the inside, we had the 2x6 service cavity. And the top right-hand corner, there's a photo here. This is the threshold for our overhead door. You can see the material in the middle dividing the concrete slab inside and out. And this is a thermal break material that was necessary to have a thermal bridge-free detail at the overhead door threshold. So the west glazing, as I mentioned earlier on, this was somewhat of a challenge for us. It was highly glazed and we weren't permitted to have any overhangs. This was again to do with the corporate guidelines. So normally it would be ideal to have some overhangs here and allow the overhangs to help us with the overheating, but yeah, it was unfortunately not possible. And when we did some analysis, we realized that this site location actually has 50% more west radiation than Germany. And you can see the hours marked there, quite a substantial amount of hours, this direct sunlight. And on the photo on the bottom left, we see there's a low amount of natural shading. There's no real trees or other buildings even close by. It's quite an open site. We did investigate planting trees, but in the end, it reduced the solar heat gain too much in the winter time. So that was also ruled out as an option. When we looked at external blinds, we were told the local site conditions were going to prove to be too windy and the building too tall to allow for external blinds here. So this would again be a typical go-to on a passive house, but again, this had been ruled out due to the site conditions. We did look at the electrochromatic glazing, but due to the large area that we were dealing with here, this was deemed too expensive. So on to our solution. Our main solution was to remove this top layer of glazing. You can see where the lighter color is there. This is glazing that has been replaced with spandrel panels. So these are insulated panels, and we've removed the glazing, but aesthetically the building will still appear very similar from the front. So this was something that was deemed acceptable by the client, and this really helped us to reduce that glazing area on the west side. And in conjunction with that, we also had automated operable internal blinds. So this was tied to temperature in the showroom, and these will open and close as required, and also leaving the occupants the option of a manual override when they so wished. And this helped to deal with the additional peak cooling load in that showroom area. So the windows themselves had a very low comfort requirement. Again, to do with our low design temperature, our UW installed needed to be below or equal to 0.61 watts per meter squared Kelvin. So this proved difficult to find, as we only had one certified cold climate window available to us and no certified cold climate curtain wall. So we did rely on window heating to meet the comfort criteria in the showroom. As you can see here marked in red, we have a heat source that's producing heat directly on the window surface itself. So any comfort issues in the winter will have been dealt with this heat source. There's some information on the windows that we chose. They're from the Wacona series. The curtain wall was the Wickline 50HI, and the windows were this WL WS 75 Evo, and the doors were the Wickline 95 doors. If anyone's looking for information on these products, I'm happy to provide you with them at the end of the presentation or afterwards. And on to the overhead doors. This is another challenging aspect of the project. So the initial design had 7 doors. You can see them here highlighted in red. So our aim was to get this number reduced. Obviously, we will consider the overhead doors to be a weak point in the thermal envelope, not only thermally, but also to do with air tightness, of course. So we came up with a design that only had 2. In the end, the client deemed it to be unacceptable. He felt like that would restrict the movement of cars in and out and around the building. So in the end, we came up with a design that the client agreed on, and it was with 4 overhead doors. So this almost 50% reduction in the number of overhead doors had multiple savings. We had the cost savings of the door themselves. We have the thermal savings for less energy loss through these weak points, and of course the air tightness was going to be greatly improved now that we have so many less overhead doors. So this was something that was thought of early on in the design stage, and it had quite a substantial impact on the building meeting the targets in the end. So I'm going to focus a little more on the overhead doors. There was a concern in the beginning that we would have a lot of air loss through the doors when in operation. So our investigation revealed there was actually minimal heat loss. It was jointly to do with the fact that doors weren't only being open maybe 10, 15 times a day. And secondly, due to the fact that the doors open and close so quickly. So this wasn't in the end a major concern for us. We had a greater concern for standby air leakage. The fact that the doors made up 17% of the transparent envelope and made up 4% of the overall wall area, we were concerned that the conventional doors, having no regard for air tightness, was that we were going to have a problem meeting our air tightness targets using conventional doors. So we had to go and look if we could find doors with an air tightness classification. Unfortunately, we couldn't find one in North America. I don't believe there is one. So we had to go to the EU to base our door selection on their classification. And one of the reasons we focused so much on this element was our building had a very low target. We were looking to go below the 0.6 of Passive House and actually achieve a 0.4. Again, as this project was in a very cold climate, it was deemed necessary to have this low target of the air tightness here to achieve our overall target. So as I said, we referred to an EU system. But the best door that we could locate in the EU was considered a class 3. And we calculated that that would increase the building's air tightness by 10%. And it proved to work. On our final test result, we had a air change per hour of 0.4. So we just met our target there. I think there was a lot of sighs of relief the day that the test was carried out. I'm going to focus a little bit more on the air tightness classification, as we did spend some time on this. We felt that by selecting a door that had been tested to this standard, the air permeability of the door, we could then calculate the total effect that the doors would have on the overall building air tightness. So basically, by having doors that met this classification, we could then see, depending on what class of door we would have, how difficult it would be to reach our target and the effect they would have. So you can see there that the class 3 door from our calculations turned out to have an 11% increase in our air tightness of the building. So the class 2 would have been 21%, and that was deemed to be too high of an effect on the building. And on the class 4 and 5, these doors, of course, would have been beneficial to have on the project, but they were either too expensive or not available. So we went with the class 3 door, but it was definitely handy to have this classification to refer to allow us to select this door and know the effect it would have before the project started. The ventilation systems and heat recovery. So for the repair shop, we had a direct vent car exhaust system. And that meant that each bay required 680 meters cubed per hour of extract air. So that was quite substantial. The original design had one fan extracting all 6 bays at the same time. So when one bay was required to extract, then all of the bays were extracting. So this was quite an energy hog on the building. And we were able to convince an engineer to run each bay on a separate fan, which resulted in an 83% reduction in the extract air requirement. So that was quite substantial. Unfortunately, there was no viable options for heat recovery from the exhaust air. We did investigate this and discuss with manufacturers if we could use their systems, but the main concern was that there would be cross-contamination within the system, and no manufacturer was willing to guarantee their product. So we did look at, as an alternative, earth tube or ground loop. Again, the demand on this would have to have had a large capacity of up to 4,000 meters cubed per hour, with an average ground temperature of 4 degrees on site, being quite low. And there was also a danger of frost heave in the building. So if we were to extract this small amount of temperature from the earth, that we could in that point then create frost below the building, and it could actually create some structural issues in the building. So the ground loop was ruled out as an option. And onto our heating cooling systems. We went with the VRF system, and the heads of this system were located in the suspended ceiling, and then they were then ducted to each room. So we did consider a residential model for cost savings, but there was a concern over longevity. So in the end, we did go with a commercial grade system. So as I said before, the system does not operate at a winter design temperature. I believe it's only for a few days in the year when a backup system needs to kick in. But we did provide an electric backup, as you can see in our drawing here. Within the VRF system, there was a backup electronic heater for those extremely cold days in winter. And the domestic hot water in the showroom, we had a very low demand. This was basically just for hand washing. There were no showers on site. So it's quite simple to provide here. We went with the sand and CO2 heat pump. And we actually located the heat pump in the repair shop. So this acted also as a cooling source, additional cooling source in the repair shop area. Then in the repair shop, domestic hot water demand, this is quite high, as each car is washed after maintenance work. So this is calculated up to 2,000 liters per day of water at 60 degrees Celsius was going to be required. Unfortunately, all we could come up with as a solution was an on-demand gas heater. And as you can see here, this had a very large impact on our PER. So we had 34 kilowatt hours per meter square per year, which made up over 50% of our building target. So we did our best to come up with a way to reduce this, and the solution for this was domestic hot water heat recovery. So the car wash load was a good candidate for the fact that it was high volume, high temperature, and the fact that it was frequently used. We did initially identify a horizontal shower type unit, and unfortunately the company stopped manufacturing due to trade issues. They were willing to create a custom unit, but they eventually abandoned it. I think there isn't a major demand for these products on the scale, so it's quite difficult to source. In the end, we went with what was designed and built as a vertical unit, but we installed it horizontally, and it was 10 foot long. So that actually turned out to be quite effective, and it reduced our domestic hot water demand quite considerably. So in summary, cold climates most definitely demand everything you've got. A simplified approach is critical. As you can tell, when we went through the doors and the overhead doors, by simplifying that approach, we made it a whole lot easier to reach our targets and reduce cost. And finding engineers who are willing to explore options, as was with the ventilation system, is a great example of how we were able to optimize the system with an engineer who was willing to explore new ways of doing things. And cold climate project innovation is most definitely required. I know there are new products coming on the market all the time, and it's important to be aware of what's out there if you're working to build a passive house in a cold climate. And think through the details early. This is most definitely key. Estimating the equipment and occupant loads, also important to do early. We were lucky on this project that the client actually has a number of car dealerships, so we were able to use values from other car dealerships to estimate our equipment loads here. It may not always be possible, but it's definitely something that should be considered early on, along with identifying all the energy flows in the building. And also bear in mind, not everything is predictable. Always add some buffer. Just aiming to reach the target is going to make it very difficult and stressful as the project progresses. There's always going to be changes, so I'd highly recommend to add some buffer to your calculations. And to close, if you like a challenge, design a passive house car dealership in a cold climate. That's all from me. Thank you very much for your time, for listening, and I'll be open to taking any questions you have at the end of today's session. Thank you.